Hypothalamus Artificial Intelligence, HI, and Research Center for Advanced Decision Technologies, RCADT, a division of HI. Digital transformation powered by real-time autonomous and intelligent algorithms. Present the conference. Planning Macro Energy Systems with Multiple Climatic Years, a Quadratic Trust Region Approach for Benders Decomposition. The material of conference was organized by the engineer Jesus Velasquez Bermudez, Ph.D. Trust Regions. Benders Coordinator Stabilization. When it is taken into account that TB iteratively solves a non-differentiable convex optimization problem, since the function Qy is a linear function of fragments, mathematical conditions related to subgradients or supergradients must be considered. From this point of view, conditions for regularization of the algorithm pitch size should be imposed to avoid oscillations and obtain stronger convergence properties. With this vision in mind, variations to the basic Benders approach have been proposed. The Benders trust region refers to a primal stabilization technique or heuristic used to speed up the Benders decomposition algorithm. It addresses the problem of oscillation, where solutions in early iterations jump sharply between different regions of the feasible set, leading to slow convergence. Core mechanism. The method restricts the search for new solutions to a neighborhood, the region of trust around the currently best-known solution. Trust region constraint. A constraint is added to the Benders master problem that limits how much variables can change from the previous iteration. Hamming distance. For problems with binary variables, the confidence region is typically defined using the Hamming distance to measure the number of bits reversed relative to the current solution. Dynamic adjustment. The radius of the confidence region adjusts based on performance. It narrows if the actual improvement is low compared to the predicted one, and it widens if the algorithm progresses well. The parameter vector x is updated iteratively to find the minimum of the function fx. Two steps are considered. A single update step k in which an approximate quadratic model mpk, dashed contour lines, of the function is minimized within a trust region of radius delta, dotted line, to determine the parameter update vector pk. B. Multiple update steps with their respective trust regions showing the convergence of the algorithm from the seed parameter vector x0 to the final parameter vector xf at the minimum of fx. The benefits of the trust region approach are: faster convergence. By keeping solutions in a trusted area, the algorithm generates more significant cuts from the start. Improved primal bounds. It helps the algorithm find high-quality, feasible solutions much earlier than standard Benders decomposition. Convergence guarantees. Although strict trust regions can sometimes interfere with global convergence, modern deployments dynamically remove or relax these constraints as the optimality gap narrows to ensure that an exact optimal solution is found. The existing literature shows that solution oscillates wildly in early iterations. Thus, trust region may be used to limit the early movements of variables, continuous, integers and/or binaries, around a previous point. Considering that BP iteratively solves a problem of a non-differentiable convex optimization due to the function Qy is a piecewise linear function, can be considered mathematical conditions related to the subgradients, or supergradients. From this point of view, should be imposed conditions of regularization of the step size of the algorithm to avoid oscillations and get stronger convergence properties. The first variation to consider is the proposal by Linda Roth and Wright, in 2001, that it is a kind of regularizing technique adapted from regularized decomposition for continuous problems which helps to mitigate two kinds of difficulties in cutting plane methods: growth in the number of cuts added to the master problem, and the fact that there is no easy way to use a good starting solution. The first variation to consider is the one proposed by Linda Roth J. and Wright, which implies minor modifications to BP. This variation limits, through a hypercube, the maximum difference between the solution of the coordinator in stage k and the solution in stage k1, introducing limit constraints in the coordinator where 1 is the scaled dimension of the hypercube. The Hamming trust region is a stabilization technique used to accelerate convergence, particularly for problems with binary decision variables. The core concept traditional Benders partition often suffers from instability, where the master problem, MP, produces solutions that oscillate wildly between distant parts of the feasible region. Then a trust region restricts the MP's search to a small neighborhood around a stability center. Why Hamming distance? For binary variables, the standard Euclidean distance is less effective for defining neighborhoods. Instead, the Hamming distance is used to count the number of binary components that differ between the current and the next solution. Planning macro energy systems with multiple climatic years, a quadratic trust region approach for Benders decomposition. To achieve objectives of the Paris Climate Agreement and limit global warming, the energy system must undergo a major transformation and replace 86% of primary energy from fossil fuels as of 2019 with renewable resources. At the heart of this transformation is renewable electricity from wind and photovoltaic, PV, for two reasons. First, the technical potential exceeds other renewables and even demand projections. Estimates for the global potential of PV alone range from 1585 to 50,580 at least 3 times 2019's primary consumption, and second, use of renewable electricity is not limited to the power sector, but can also be deployed for electric heating, mobility, and the creation of synthetic fuels to decarbonize the heat, transport, and industry sector. This paper applies Benders decomposition, BD, to two-stage stochastic problems for energy planning with multiple climatic years, a key problem for the design of renewable energy systems. A BD was first developed with a simple continuous master problem, and few, but large, subproblems. Next, a trust region method, BDTR, was developed using a quadratic constraint that is continuously adapted to further improve the algorithm. In a quantitative case study, BDTR accelerates BD by a factor of 4 to 6, slightly increasing the time to solve the master problem but greatly reducing the number of iterations. With adequate computational resources, BDTR outperforms closed optimization if the planning covers more than 6 climatic years, because, thanks to distributed computing, the execution time does not increase with the number of scenarios. In addition, the results show that BDTR benefits from an initial heuristic solution, but its performance does not depend on it. Finally, the authors suggest further improvements. First, heuristic methods to narrow the solution space of the master problem, and second, approximations of the subproblems by adding in exact, but valid and fast cuts. The image presents technical information about the quadratic stabilization of the project planning macro energy systems with multiple climatic years. Equations 1a to 1j provide the closed formulation of the two-stage stochastic energy planning problem. The complete model is presented in the section 3. It includes multiple regions of expansion and operation. Between regions, the model can build transmission capacity in the first stage to exchange energy in the second. Distinct energy carriers, like electricity and hydrogen, may be converted into one another by respective technologies, such as hydrogen turbines or electrolyzers. Finally, storage losses and additional constraints, imposing upper limits on capacities or restricting operation, for instance a yearly emission limit. For the set of technologies, the model decides on the expansion of capacities over a set of years. All variables of the problem are continuous and non-negative. The restrictions have the following interpretation. 1a is the objective function of the problem in minimizing the total system costs composed of the expansion costs and the sum of the operating costs over all years and scenarios, weighted according to the probabilities of the scenario. In 1b the expansion costs depend on the expansion variable and the specific expansion costs of each technology / In 1c the operational costs depend on the costs associated with loss of load class and variable costs of generation technologies, for instance fuel costs. 1d is the capacity available in each year, depends on expansion in the current and previous years. 1e to 1 hour these capacities constrain the operation of technologies at each time step t, in each scenario s, and within each year. For generation technologies, the capacity constraint includes a scenario-dependent capacity factor reflecting the available share of capacity. For storage technologies, 2 different capacities constrain 3 different operational variables. Charged energy and discharged energy are both constrained by the power capacity. The current storage level is constrained by the energy capacity. In 1i net supply from generation and storage technologies must match the exogenous demand in each year, time step, and scenario, as expressed in the energy balance. To avoid infeasibility, the balance includes a loss of load variable. 1J. Calculate the storage tier in a time step t based on the level at the previous time step, plus charged and minus discharged energy. The storage restriction is circular for each year, which means that the last time step in a year is before the first. The figure shows an illustrative representation of the planning problem based on the block structure of the constraint matrix, of closed two-stage problem. The expansion problem in the first stage includes expansion and capacity variables and constraints. The second stage includes the remaining constraints, namely the energy and storage balance, the definition of variable costs, and the capacity restrictions. The latter links capacity with operational variables and connects first and second stage. The figure shows the graph of years and scenarios for an example problem. For BD, first stage expansion corresponds to the MP, while operation is split into several independent SBs. Consider a problem covering 2 consecutive years, 2030 and 2040, and 2 scenarios, representing the climatic years 2000 diaresis and 2008 diaresis. According to the problem formulation in the previous section, operation is modeled for each year and scenario, resulting in 4 distinct operational problems. The figure provides the structure of the decomposed problem. It shows how the operational problem is split into 4 independent SBs, each consisting of different operational variables, but sharing capacities with the MP and other SBs for the same year. Splitting second stage operation into several SBs is beneficial, because it enables distributed computing and prevents complexity in the second stage too. Scale with the number of scenarios. In addition, it increases the number of cuts added to the MP in each iteration, improving convergence, as we will elaborate when introducing the BD algorithm. The image presents technical information about the quadratic stabilization of the algorithm. BD often suffers from slow convergence and solutions oscillate between the edges of the feasible region. In this case, this problem is pronounced, because the feasible region is hardly restricted and completely continuous. As a result, the algorithm moves very slowly from the edges to the optimal solution, like getting to the center of a sphere by making thin cuts from alternating sides. The stability problems of BD are well acknowledged and addressed by various trust region approaches. The key idea of these approaches is to avoid oscillation by restricting the feasible region artificially. There are 2 ways to achieve this by adapting the MP. 1. Add a restricting constraint. For binary problems, the norm or Hamming distance can restrict the MP to a radius around a reference solution. Continuous problems can use the infinite norm that does not create a radius but limits the maximum step size across all variables compared to a reference. In both cases, the radius or maximum step size can be refined during iteration. 2. Extend the objective with a penalty term. To penalize deviation from the reference, the approach extends the objective with the 2 norm, or Euclidean distance, creating a quadratic problem. The proposed method combines both existing trust region approaches, add a constraint restricting the MP to a radius around a reference solution but use the Euclidean instead of the Hamming distance since the MP is continuous and not binary. The figure shows the trust region adaptation during iterations. It includes 3 unbounded expansion variables, restricted by a spherical trust region. The optimal solution is indicated in green, the current best in orange, and the solution at the current iteration in yellow or red, depending on whether it improves the current best or not. The first iteration in A results in an objective above the current best, but the trust region is binding and remains unchanged. Due to the added cuts, the second iteration, B, improves the current best and the trust region is consequently recentered for the third iteration. Therefore, its radius is also adapted based on the norm of the new solution. The third iteration in C does not improve the current best, but the trust region is not binding anymore, and its radius halved accordingly. The fourth iteration with a smaller trust region in D does not improve the solution. The image presents technical information about scenarios for climatic years. To compare the introduced variations of BD, the model was solved as a 2-stage planning problem with multiple scenarios. Each scenario represents a climatic year with different patterns and total levels of electricity demand and capacity factors for wind and PV. For this purpose, we build on corresponding data for 39 climatic years from 1980 to 2018 based on reanalysis data from the NASA's MERA-2 dataset. Stochastic programming often reduces N scenarios of historical data, in our case 39 climatic years, to a smaller number that captures the empirical distribution but improves computational tractability. Scenario reduction methods determine a set of representative scenarios S and a set of corresponding weights such that the weighted scenario average of second stage costs approximates the sample average over all scenarios. The figure illustrates the results of the clustering algorithm for M equals 6. Each color represents a group and the node of the representative scenario for this group is equipped with its weight that reflects the relative group size. The color and thickness of connecting lines between the nodes indicates similarity, the inverse of the distance. The figure introduces all considered technologies, depicted as gray circles, and their interaction with energy carriers, depicted as colored squares. Exogenous demand in the model is limited to the carrier electricity, which is modeled at an hourly resolution for the entire year. Hydrogen uses a daily resolution, oil and gas a yearly resolution. In the graph, entering edges of technologies refer to their input carriers, outgoing edges relate to outputs. For example, the generation technology electrolysis uses electricity as an input to generate hydrogen. Storage technologies, like pumped storage, have an entering and an outgoing edge to represent charging and discharging. Beyond pumped storage, the model includes batteries for short-term and hydrogen tanks for long-term energy storage. Including these technologies is critical due to their importance for decarbonized systems and their impact on the structure of the planning problem. The image presents technical information. The algorithms. Algorithm 1, Parallelized Multi-Cut Benders, based on Conejo et al. In 2006. Algorithm 2, Parallelized Multi-Cut Benders with Dynamic Quadratic Trust Region. The figure demonstrates the substantial speedup the trust region approach achieves over the standard algorithm, decreasing the solution time by a factor of 4 to 6 depending on the number of scenarios. The acceleration results from greatly reducing the number of iterations, which outweighs the increase in time per iteration due to the added quadratic constraint. With 2 scenarios, for instance, average time per iteration increases from 22 to 30 seconds when using the trust region method, but at the same time the number of iterations drops from 1438 to 181 when initializing the trust region and to 279 when not. Initializing the trust region only has a minor and inconclusive impact on the total solution time. Increasing the number of scenarios does not have a consistent effect, because all algorithms are completely parallelized. The figure shows the runtime to generate and solve the problem for closed optimization using between 2 and 16 scenarios. Generation and solve time both increase exponentially with the number of scenarios, but solve time has an outlier at 12 scenarios. The outlier was reproduced several times and likely results from the mechanics of the barrier algorithm. The figure shows the runtime to generate and solve the problem for closed optimization using between 2 and 16 scenarios. Generation and solve time both increase exponentially with the number of scenarios, but solve time has an outlier at 12 scenarios. The outlier was reproduced several times and likely results from the mechanics of the barrier algorithm. Albert Einstein thought that imagination is the highest form of research. Thank you for your attention.